music. We discussed last episode, praise be to God, Prophet Muhammad. O God, there is nothing easy except what you make easy. O Lord, make it easy and remove worry. We discussed Muhammad for God, and peace be upon the messenger of God, Prophet Muhammad. We discussed the transformer protection scheme. Protections vary by transformer size and importance. This lecture focuses on the transformer vector group and its scientific details, inspiring our nation's renaissance. In episode 4, we explained differential protection issues like natural differences between incoming and outgoing currents. Primary and secondary currents differ due to winding turns. In episode 4, we discussed differential protection for transformers, focusing on issues such as differences in currents. The primary and secondary currents differ due to the number of turns in their windings. Additionally, the connection type of three-phase transformers, such as star-star, star-delta, or delta-star, affects the relationship between primary and secondary currents about the number of turns, the secondary winding of the transformer. Three-phase transformer connections affect currents differently. Differential protection issues arise with tap changes during operation, as each tap changes current values, possibly causing arcs. Incorrect tripping can result from inrush current at startup or sympathetic inrush. One of the problems with differential protection for transformers is that some transformers are equipped with what is called a tap changer, which is often of the type used while the transformer is in service. It is known that each tap has its own specific current, so when we switch from one tap position to another, the current value will change from one value to another. During the tap change, an electrical arc may occur, which also affects the differential protection. The tap changer is used on the high voltage side due to lower current. Incorrect tripping is inrush current occurring at start or during sympathetic inrush. We explained these earlier, but today we focus on points needing compensation factor when testing differential curve, vector group, and zero sequence elimination. We explained most of these points in detail earlier, but in today's lecture, we will focus on the points that require a compensation factor when testing the differential characteristic curve, which are the vector group and zero sequence elimination. When testing the differential characteristic curve, the factor group is zero resolution. Inspirational elimination. It is well known that three-phase transformers have two sides. The first side is the primary windings, winding 1, and the other side is the secondary windings, winding 2. These windings are wrapped around the same iron core. Single-phase transformers can also be used and connected externally to achieve the same results as a three-phase transformer. Transformer windings, whether primary or secondary, are connected in star or delta configurations. In a delta connection, each winding's end connects to the next winding's start. In a star connection, winding ends or starts are joined together. Primary windings connect to the power source, and secondary windings connect to loads, indicating power flow direction, not voltage level. The primary winding is linked to the power source, and the secondary winding to the loads, regardless of voltage. Power typically flows from primary to secondary. Primary and secondary windings can be connected in delta or star independently. Primary windings connect to the power source, and secondary windings connect to loads, indicating power flow direction, not voltage level. Power typically flows from primary to secondary. In operation, energize primary first, then secondary. Disconnect secondary first, then primary. For step-down transformers, energize high voltage side first, then low voltage. There is no relation to the voltage level on each side. Therefore, the primary winding is the part connected to the power source, regardless of whether it is high voltage or low voltage, while the secondary winding is the part connected to the loads, regardless of whether it is high voltage or low voltage. Direction of power flow is usually from the primary side to the secondary side. Operate transformers by energizing primary, then secondary windings. Disconnect in reverse. In substations, energize high voltage first, then low. Disconnect low voltage first. Solar plant transformers, step up by day, step down by night. Now let's return to connecting windings. Located in or at substations. First operate the A, then the When disconnecting this transformer, we first disconnect the low voltage side and then the high voltage side. In the case of transformers used in solar power plants, they operate as step-up transformers during the day and as step-down transformers at night. Now, let's return to the method of connecting the primary and secondary windings of transformers. The way the primary and secondary windings are connected determines the angle between the primary voltage and the secondary voltage. This angle is referred to as phase displacement, or it can also be called angular displacement. So, phase displacement is the angle between two voltages. Displacement is the angle between voltages, positive if low voltage leads, negative if it lags. This refers to phase 2, neutral, real, or imaginary. The angle is positive if low voltage leads high, negative if it lags. Phasor diagram is counterclockwise per IEC 600-761. This angle is positive if the low voltage leads the high voltage, while it is negative if the low voltage lags behind the high voltage. Here, we describe the leading and lagging of the low voltage only because we considered the high voltage as the reference voltage that does not lead or lag. We assume the phase sequence rotation of the power source is ABC. Applied on the high voltage side, the phasor diagram rotates counterclockwise, a globally accepted standard per IEC 600-761. Some references compare the phase shift between the high and low voltage sides. OEC. Observe the phasor diagram as it rotates counterclockwise. Phase A appears first, followed by B, then C, repeating ABC. Some references compare the phase shift between high and low voltage sides, noting a 30-degree difference. Transformer winding connections are categorized into vector groups based on phase displacement. If both transformer sides are connected similarly, like star-star or delta-delta, the secondary and primary voltage wave angles will align, resulting in zero angle difference. It is well known, as everyone knows, that there is approximately a 30-degree difference. Based on the value of the phase displacement angle, the connections of the transformer windings are divided into several directional groups called vector groups. If the windings on both sides of the transformer are connected in exactly the same way, such as saying star-star or delta-delta, then the angle of the secondary voltage wave will either be the same as the angle of the primary voltage wave, which means that the angle difference between them will be zero. Group 1, zero phase displacement, YY0 or DD0. The secondary voltage can be opposite to the primary by 180 degrees, called out-of-phase shift. Group 2, YY6 or DD6, showing 180-degree displacement. If the connection differs between high and low voltage windings, like star to delta or delta to star, the low voltage wave shifts 30 degrees from the reference high voltage. Things were no voltage windings, so it was the first and second. Low voltage shifts 30 degrees from high voltage. Reference voltage angle is fixed. Angle 30 degrees is third group. Angle plus 30 degrees is fourth group. So, if the angle is 30 degrees, it falls under the third group with its symbols. If the angle is plus 30 degrees, it falls under the fourth group of directional groups with its symbols. These four groups, the displaced month who removes her DY11, DYD11. The four groups, the most famous of them, but not all, describe the vector group according to the European standard IEC 600-761 using letters and numbers. The first letter indicates the connection of the high voltage windings and is written in capital letters, while the second letter indicates the connection of the low voltage windings and should be written in small letters. Then we follow it with numbers from 0 to 11. Clock hands move 360 degrees in 12 hours. Each hour is 30 degrees. Numbers 1 to 6 show lagging low voltage, 7 to 11 show leading. Number 0 means low voltage aligns with high voltage, no lead or lag. 60 degrees, 12:30. The numbers from 1 to 6 mean that the low voltage angle is lagging behind and is negative. The numbers from 7 to 11 mean that the low voltage angle is leading and is positive. The angle or number 0 means that the low voltage angle is identical to the high voltage angle in phase, so it is neither leading nor lagging. The one that changes and moves is the low voltage, which is closer to the short hour hand, while the high voltage is fixed at 12. which is closer to the long minute hand. The length of the vector indicates its value. The even numbers mean that the connection of the high voltage must match or resemble the connection of the low voltage, such as saying star or delta. On the other hand, the odd numbers mean that there should be a difference between the connection of the high voltage and the connection of the low voltage, such as saying star delta. Subscribe to the channel. A torn star, so it commands the delta connections. Notice homeland. The capital letter N, or the small letter n, is used next to the letter representing the terminals of the windings connected in a star configuration to indicate that a neutral point has been connected to ground. However, if it is not mentioned, this means that it is not possible to access the neutral point through this bushing. The small letter A is used in autotransformers and refers to the low voltage windings. DYN1 means delta high voltage, star low voltage. The small letter A is used in autotransformers and refers to the low voltage windings. The vector group DYN1 means high voltage windings are in delta, low voltage in star with grounded neutral N. If N is absent, the neutral is ungrounded, isolating the system. Low voltage lags high voltage by 1 hour or 30 degrees. Lagging means vector A capital appears first, then vector A small after 30 degrees. This star has a grounded neutral point through the small n. As we said, if the letter N is not mentioned, this means that the neutral point of this star is not grounded, meaning that the system has become isolated from the ground. The low voltage wave is lagging behind the high voltage wave by 1 hour, which means it is lagging by 30 degrees. We can describe it by writing 30 degrees lag. The term lagging here means that if you look to the left, you will first see the vector A capital, which represents the voltage, and then, after 30 degrees, you will see the vector A small, which represents the voltage. If I tell you the vector group for this transformer is WEND11, indicating the high voltage windings form a star with a grounded neutral point while the low voltage windings form a delta. The low voltage wave is leading the high voltage wave by 1 hour, or plus 30 degrees, or simply 30 degrees lead. Rotating the phasor diagram for both high and low voltage vectors in space counterclockwise in the ABC phase rotation system, the low voltage vector appears first as A small. After 30 degrees, the high voltage vector appears as A capital. This table summarizes the vector group and its corresponding phasor diagram for various types. Assuming clockwise rotation, it is called ACP phase rotation or negative sequence rotation. This means you will see the vector. The low voltage vector, a small comes first. After 30 degrees, the high voltage vector, a capital follows. Vector A appears first, then C and B maintaining ACB order. If the rotation is clockwise, it's called ACP or negative sequence rotation. Vector A appears first, then C, then B, maintaining ACB order. Looking right, A is small for low voltage lagging by 30 degrees in YMD11. Whether the sequence is positive or negative is crucial for determining the signal's nature. First A, then C, and then B, maintaining this order ACB. This means that the direction of rotation will be completely different in the vector group. In other words, if you look to the right, you will see the A small for the low voltage lagging by 30 degrees in the YMD11. This indicates whether the direction of rotation for the phasor diagram of the power source is in positive sequence. It's very important in determining whether the signal is positive, negative. It's very important in determining whether the signal is positive or negative. An inspiring national renaissance. If there is, it can be created negative sequence through by swapping any phases with each other, like switching between A and B, or notice with me that when the system was balanced among the 3 phases, it only shows, while the rest, a hammer of a combiner. A negative sequence was a 0 sequence. Negative sequence 0, swap phases same. It equals 0, and when we swapped or exchanged with the 3 in the balanced system, we got. And when we swapped or exchanged with its family, the sequence was also, and thus we conclude that from the same single recommendation, we can obtain, and when we swapped or exchanged with its family, sequence was also, and therefore we conclude that from the same single recommendation, we can get, I am 1, and I am 1, and I am 1, and I am 1, and I am 1. By swapping phases, we move from 1 to 11. When connecting two different transformers in parallel, one can be adjusted to match the other by swapping phases on either or both sides. This conversion applies only within odd or even numbered vector groups, not between them. The table shows how to adjust transformer connections to convert vector groups, though it's challenging at high voltages. It is possible to convert between number 5 and 11 via connection. If two transformers differ, for parallel connection, one can be adjusted to match the other without internal changes. Use one as reference, swap phases on primary, secondary, or both of the other. Convert within odd or even vector groups, not between them. Table guides vector group conversion, especially in parallel, challenging at high voltages. Understand? Don't just memorize. Use a program to analyze angles in parallel connection, first as reference. This conversion is between the connections of vector groups with odd numbers and even numbered connections. You cannot convert an odd-numbered vector group with an even-numbered one. The topic isn't just memorizing steps. You can put both transformers into a program and run it to observe and analyze the angle readings when connecting both transformers in parallel. You will notice that we want to connect two transformers in parallel, with the first transformer being the reference for the second. Note that the phase shift of the vector group is crucial. So the topic isn't just about memorizing steps without understanding them. You can easily put both transformers into a program and then run the program to observe and analyze the angle readings when connecting both transformers in parallel. You will notice that we want to connect two transformers in parallel, with the first transformer being the reference for the second. Please note with me that the displacement of the final object is carefully considered. Transformers must match angles. One advances 30 degrees. Y1 is delayed by 150 degrees. As we mentioned before, each hour corresponds to 30 degrees. So 5 hours correspond to 150 degrees, which is 5 times 30. Our goal is for both transformers to have exactly the same angles, so that we can connect them in parallel. Because if they are connected as they are without any changes, it will create what is called eddy currents circulate between the transformers, even if the load is disconnected. And of course, this current represents an undesirable power loss, and additionally, the load on both transformers will not be balanced. This means that there could be an overload on one transformer without the other, and it might trip. Notice with me that when connecting both transformers in parallel on a simulation program and then running the program, the angle of the first transformer is definitely for him. It is 24 degrees, while the angle of the red phase is minus 155 degrees. Now, we switch the yellow phase with the blue phase on the L side to try. Assuming that this is our reference, we will run the program again. It is important to note that there are still differences between the voltage angles. Between the transformers, we observe that the angle of the red phase in the first transformer corresponds to the angle of the yellow phase in the second transformer, and the yellow phase in the first transformer corresponds to the yellow phase in the second transformer. We are swapping the red phase with the yellow phase in the second transformer, and we will run the program again to ensure that the angles of the transformers are now correct. Notice now how the angles have aligned between the two transformers, which is required for operating the transformers in parallel. The choice of the appropriate vector group depends on several factors. It must be considered when conducting various studies. Before establishing any power station, one must study the harmonic ratio and remove it. A method for eliminating harmonics in the network involves making them cancel each other out. Each harmonic has a value and angle. Summing these harmonics to a vector sum of 0 eliminates them without filters. This requires studying transformer connections. Parallel transformers must share the same vector group and meet conditions. Study the protection system, including ground fault detection, as delta or star configurations isolate from the ground, making fault currents low. Also, examine nonlinear loads like electric furnaces. It's important to study whether the transformer will be connected in parallel or not. All transformers connected in parallel must have the same vector group, and other conditions for connecting transformers in parallel. Additionally, it's crucial to study the protection system and whether it includes ground fault detection or not, as it is not possible to detect ground fault currents If the transformer is connected in a delta or star configuration, it is not exposed because it is considered isolated from the ground, and the fault current in this case is very low. 4. Study the nature of nonlinear loads, such as electric furnaces or... This is because they generate harmonics, so transformers with a suitable vector group are needed to minimize harmonic impact. 5. Connect transformers near the generation source in a delta configuration to prevent unbalanced conditions from transferring. Delta connections prevent harmonics from passing through, preventing vibrations. 6. Connect transformers near loads in a star configuration to provide a neutral point for consumers. 7. Use transformers in the Y configuration to facilitate network interconnection. Additionally, that it effectively prevents passage or their multiples passing through it to avoid causing violent vibrations in the generator. 6. Preferably connect the windings of transformers close to the loads in a star configuration to offer a neutral point. 7. Preferably use transformers in the Y configuration to ease all network interconnection. Also, easily create and avoid a neutral point. Using star connections reduces insulation costs since star voltage is lower than delta by 3. It is preferable to use a vector group of type Y. I am able to create a point where it can easily be brought up and avoided as much as possible. Using star connections reduces insulation costs as the voltage in the star configuration is lower than in the delta configuration by 3. Prefer using a vector group of type Y in distribution transformers to prevent harmonics transfer from the loads to the grid through the delta, especially odd ones, and prevent ground fault currents affecting the grid. In distribution transformers, this is to prevent harmonics from transferring from the loads to the grid through the delta, especially the odd harmonics, in addition to preventing ground fault currents from affecting the grid. Subscribe to the channel. An inspiring leader of the nation, if there is a step-up transformer at the generation side, with a vector group of YD1 where the delta side has the lower voltage, this means that the voltage wave on the high voltage transmission line will lead by an angle of 30 degrees, because a lag of 30 degrees means relatively. The high voltage EADS, assuming that the reference is the voltage, which is the generation voltage, means I can either say that the delta is at an angle of minus 30 degrees. With the star at 0 degrees, the delta is at 0 degrees, with the star at plus 30 degrees. We use a transformer with a vector group. The Y receives the incoming Y voltage, delaying the delta side voltage angle by 30 degrees. If I told you the vector group of the transformer is where the Y receives the incoming Y voltage, which means that the voltage angle on the delta side will be delayed by 30 degrees, thus making the final voltage angle 0. It is estimated at 30 degrees, and then it lags by 30 degrees, and it returns as it was originally intended. If I told you that the vector group of the transformer is this transformer has 3 windings. The first and second are high voltage windings in a star configuration grounded to the earth. The third, marked TV, is in a delta configuration used for auxiliary power, testing, and stabilization, also in a star configuration grounded or connected to the earth. While the third is called the winding. The third winding, typically in a delta configuration, serves multiple purposes as an auxiliary transformer for station loads, for testing power transformers, and as a stabilizing winding to manage harmonic currents. Its necessity lies in preventing induction exposure. Electromagnetic induction occurs from voltage on one winding and mutual induction, while electrostatic induction arises from capacitances between windings or with the ground. The latter is more dangerous due to disturbances in capacitance values due to shocks or malfunctions. To find paths for the third harmonic currents during ground faults or during unbalanced loading. As for the necessity of the winding, as shown in this image, the reason is that leaving the winding ungrounded, or in other words, will expose it to 2 types of induction. One is electromagnetic induction, which results from having voltage on one of the windings and mutual induction between them. Another type is called electrostatic induction, which results from the various capacitances between the windings themselves or between the windings and the ground. The danger of the second type increases compared to the first, due to the disturbance in the value of these equivalent capacitances, and for various reasons, such as the transformer being exposed to an electric shock, for example, or experiencing a malfunction in the loads, when not all poles are operating together during opening or closing. Also, in case of boundaries given by the ground or between the phases, all of the above may lead to, if the delta file is not dated, Very high instantaneous voltages may exceed the rated value, which could lead to the destruction of its insulation. Therefore, it is always recommended to connect one of its terminals to the ground when there is no load on it. However, if it is used to feed loads, it is connected through a surge resistor to avoid the aforementioned issues. This image shows us a main plate of a transformer, so we can convert from 230 kilovolts to 33 kilovolts using windings. One more thing, voltage, and we can also convert from 230 kilovolts to 11 kilovolts using high voltage windings. Also, notice how the delta is exposed. And for those who want to dive into the world of power transformers and get into the details, they should refer to this standard for the IEE. Related to power transformers and delving into their details, refer to this standard for the IEE. Translation by Nancy Ponkar. Inspiring. The Renaissance of a Nation. Testing transformers ensures connections between high and low voltage sides match specifications. Voltage is applied to the high voltage side through a noose or disconnecting it. If a fault occurs, an independent generator or ACDB cables are used. A jumper connects high and low voltage windings to equalize voltage difference. Phasor diagrams are applied for each winding based on jumper placement. Before testing, all voltage sides connect to a test block with wooden pieces and nails for safe measurements, avoiding direct contact with the transformer. If any fault occurs during the test, we get voltage from a generator or ACDB. Then we connect a jumper between a high and a low voltage winding to equalize voltage. After that, we apply phasor diagram based on jumper placement. Connect high and low voltage sides to test block. This block, made of wood and nails, conducts measurements safely. Where do we connect the jumper? We notice that both points. So we connect all the high voltage and low voltage sides to the test block. This block consists of regular wooden pieces with a set of nails for conducting measurements through it, not directly on the transformer itself, to avoid any electric shock by mistake while measuring on the transformers. So where do we connect the jumper as shown in this image? We notice that both points have become one point, and then we turn on the system, and using a regular method, we measure the voltage difference between them, and then we measure the voltage difference between. They became 1 point, and then we turn on the system, and using a regular method, we measure the voltage difference between, and then we measure the voltage difference between, should be, what are you doing? The same great soldier that he is, the small voltage minus the return. And if the vector group recommendation is, we connected a jumper between high and low voltage, matching them. It will look like this. Measuring the voltage difference with a multimeter, the expected difference is the sum of the big and small voltages. Notice in this phasor diagram that the vector length has increased proportional to its value. The result so far is that if the voltage difference between the high voltage plus the small skin, where you can notice with me in this phasor diagram that the length of the vector has increased, and it is known that the length of the vector is proportional to its value. The result we have obtained so far is that if the voltage difference is less than the highest voltage on each phase individually, and the vector group is, and if the voltage difference if the vector group is Y and Y6, then the highest voltage on each phase individually is higher. However, if the vector group of the transformer is of type DYN11, we create a jumper between one phase on the high voltage side and one phase on the low voltage side, as shown in this image. Draw phasor diagrams for each side. Connect 1U to 2U. Measure voltage differences between high and low voltage windings. Compare with phasor conditions. 1U to 1V equals 1V to 2N plus 2U to 2N. 1V to 2W should match 1V to 2V, and 1W to 2V should exceed 1W to 2V. If table values meet these conditions, the transformer vector group is DN11. This table shows DYN11 results. The voltage difference between 1U and 1V equals the sum of differences between 1V and 2N and 2U and 2N. The difference between 1V and 2W should match that between 1V and 2V, and the difference between 1W and 2V should exceed that between 1W and 2V. If table values meet these conditions, the transformer vector group is DYN11. This table shows the practical results of testing the DYN11 vector group. Before testing, isolate or disconnect the neutral from the ground to prevent jumper temperature rise or burning. The fuse fuse or MCCB rated current should exceed the magnetizing current when applying 415V to the transformer. Typically, magnetizing current is about 1% of the rated current at high voltage. First, find the high voltage rated current, take 1% of it, and reverse this value for 415V application. Isolate the neutral before the vector group test to prevent overheating. The fuse or MCCB's rated current must exceed the magnetizing current at 415V, typically 1% of the rated current. Calculate the high voltage rated current, take 1% and adjust for 415V. The rated current value of the fuse or MCCB should be greater than the magnetizing current value that may arise when applying 415V voltages to the transformer. The magnetizing current value is usually equal to 1%. The rated current value when applying rated high voltage. We first find the high voltage rated current value, then take 1% of this value, and then reverse this value in the event of applying 415V voltages. 415 volts through ratio and proportion. If the rated high voltage gives a certain magnetizing current, what will it be at 415V? It depends on the measured voltage, which could be 415V, 400V, or 380V. For a DYN1 transformer vector group, create a jumper between phases on the high and low voltage sides as shown. Measure and compare voltages to ensure the vector group is DYN1. The first condition, the voltage difference between 1U and 1W equals the sum of differences between 1W and 2N and 2U and 2N. The second condition, the difference between 1W and 2W matches that between 1W and 2V. The third condition, the difference between 1V and 2W is greater than between 1V and 2V. The jumper's exact placement doesn't matter. All voltage measurements must be made and compared to these conditions exactly as in the previous method to ensure that the vector group is of the DYN1 type. The first condition is to ensure that the voltage difference between 1U and 1W must be the sum of the voltage difference between 1W and 2N. Ensure the voltage difference between 1W and 2W equals that between 1W and 2V. Ensure the voltage difference between 1V and 2W exceeds that between 1V and 2V. Jumper placement is flexible, but must be reversed on the phasor diagram. Vector group test focuses on comparing resulting values with conditions, not transformer ratio. Refer to the attached file for detailed test information. Determine vector group by redistributing currents and comparing them. What type of vector group does this connection shown in the diagram represent? The jumper doesn't have to be between 1U and 2U. Place it anywhere. Reverse its position on the phasor diagram. The vector group test checks resulting values, not the transformer ratio, ensuring conditions are met. If asked to determine a connection's vector group, redistribute currents on transformer terminals and compare. What vector group does the diagram's connection represent? Assume currents enter from the delta side and exit from the star side with the power source on the delta side. Treat each phase as a single-phase transformer. It contains details about testing each connection, and you can refer to it if you want more information. The last topic we can discuss in today's lecture is that if you have a connection and you are asked to determine its vector group, this can be done by redistributing the currents on the transformer terminals and comparing them. For example, what type of vector group does this connection shown in the diagram represent? Currents enter delta, exit star, power to delta, loads to star. Treat each phase as single-phase transformer. Current enters primary, exits secondary. Kirchhoff's law unifies delta current. IR small plus IR capital. When current enters the primary side, it exits the secondary. We unify current direction in the delta winding. IY is the sum of IR small and IR capital. IR small is IY minus IR capital with 1 ampere. IY is 1 ampere at 120 degrees and IR capital is 1 ampere at 0 degrees. The result is the square root of 3 at 150 degrees. Low voltage current is delayed by 150 degrees. What vector group does this connection represent? Is it DY1, 3, 5, 7, or 11? IY capital minus IR capital. IY is 1 ampere at 120 degrees. IR is 1 ampere at 0 degrees. Result, 3 at 150 degrees. If high voltage current is the reference, its angle is 0, delaying low voltage current by 150 degrees. Every 30 degrees equals 1 hour, so 150 degrees equals 5. Every 30 degrees equals 1 hour, so 150 degrees equals 5 hours, making the vector group YD5. What vector group does this connection represent? Is it DY1, 3, 5, 7, or 11? Assume balanced star-side currents. Determine current direction in the delta and apply Kirchhoff's law at a corner. The small plus capital current equals the small y current, so capital current equals small y minus small current. Thus, 1 at 120 degrees, IY small minus 1 at 0, IR small equals 3 at 150 degrees. From the phasor diagram, the high voltage wave leads the low voltage wave by 210 degrees, indicating a DY7 connection. Alternatively, the low voltage wave lags by 210 degrees. If it were DY5, the high voltage wave would lead by 150 degrees. Therefore, 1 at an angle of minus 120 degrees, which is IY small, minus 1 at an angle of 0, which is IR small, will equal the three-dimensional square root of an angle of minus 150 degrees. Therefore, we will notice from this visualization that the high voltage wave is 10 degrees ahead of the low voltage wave. Therefore, the recommendation for this vector group is DY7. It can also be said that the low voltage wave will be 210 degrees behind the high voltage wave, and if the vector group was of the DY5 type, the high voltage wave would be 150 degrees ahead of the low voltage wave. It can also be said that the low voltage wave is 210 degrees behind. The high voltage wave leads by 150 degrees. Notice the difference between the two connections, the DY7 connection and the DY5 connection. I hope the concept of the vector group for transformers has become clear and simple for you. Stay tuned for the next episode, where we will explain how differential protection deals with all these differences in connections and how it remains stable regardless of the type of vector group. Wishing you all the best and hope everything goes well. See you very, very soon.